Hi everyone. We are going to talk today about probability and specifically chapter 5.1. We're going to introduce chapter 5 and then we're going to talk about 5.1. So today we're going to use simulation to model chance behavior and to estimate probabilities. We're going to start with an introduction to probability, and we're going to talk about different ways that we can calculate probabilities via observation, simulation, and then using a probability model. So we're going to talk about, in addition, we're going to talk about the law of large numbers, and then we're going to focus on using simulation. So again, chapter 5 is called probability, and then section 5.1, which is what we're going to talk about today, randomness, probability, and we're going to focus on simulation. So our goals are going to be to interpret probability as a long-run relative frequency and use simulation to model chance behavior. So here's just our little introduction to the chapter. So here's a quote at the top here. When we produce data by random sampling or randomized comparative experiments, the laws of probability answer the question, what would happen if we repeated the random sampling or random assignment process many times? And we kind of touched on this in chapter 4. But so in this chapter, we're going to focus on that probability and figuring out, like, how do we use probabilities? How do we use our probability theory to calculate probabilities to be able to determine if our results are statistically significant or whatnot? So anytime we have a question involving chance, we have 3 options in answering that question. So in other words, we can find probabilities 3 different ways, or I should say estimate probabilities 3 different ways. Option 1, observation. That means observing the random phenomenon, actually going out and doing the experiment, flipping the coin, rolling the die, whatever that might be. Option 2, simulation. So we've talked a lot about simulation, since like the beginning of the year. So using a table of random digits or imitating a procedure based upon a model that accurately reflects the event. So something like, drawing random numbers out of a hat, things like that. We're going to focus on these 2 things, 1 and 2, observation and simulation in this section, but then the majority of the chapter will be about probability models, a mathematical description of a random phenomenon. So in other words, like the theoretical probability. So first, observational probability. So here's an experiment that we're going to talk about a couple times in this lesson. So if we were to toss a coin 10 times, so we're tossing a coin 10 times, what's the likelihood of getting at least 3 consecutive heads or 3 consecutive tails? So take a minute, think about what that really means. You're tossing a coin, and maybe, the first toss you get a heads, and then maybe the second one you get another heads, and then maybe the third one you get a tails, something like that. But you toss the coin 10 times total, and you record in order, heads, tails, whatever. So what's the chance of getting at least 3 consecutive heads or 3 consecutive tails? So 3 in a row. I want you to think about this, pause the video if you need to, and make a little prediction. What do you think the chances are? What's the probability of that happening? So if we wanted to kind of estimate, so essentially we can calculate that theoretical probability, and we will later in the chapter. But for now, we're going to start with observation and simulation. So if we wanted to estimate this probability using observation, we would actually grab a coin and toss the coin 10 times. And then you're going to record a success if you got at least 3 consecutive heads or tails, record a fail if you did not get at least 3 consecutive heads or tails. Each time you toss the coin 10 times, that's called one trial. And then you're going to basically repeat this. I wrote 9 times, it could be 10 times, it could be 100 times, whatever. If we were in person, if we were in class, I would actually have you do this, okay? So, and then we're going to combine the number of successful trials you had with all of your classmates' results. And we're going to use all of those results to to estimate the probability of getting at least 3 consecutive heads or 3 tails in the 10 tosses. And this is our observational probability. So these are some results from my class from a previous year. So here's their observation. So you can see they each did 10 trials. So each of these like lines in this table here, and we kind of ran out of room, so we put 2 of these lines at the top here. But each line in this table represents one person, or one, I think it was partnership, okay? So each of them did 10 trials. So for example, let me start here at the top. So this one partner, they flipped their coin 100 times, essentially. So like 10 times 10. And 7 of those sets of 10 flips had at least 3 consecutive heads or tails. So we label them as successes. 3 of those, we did not have at least 3 consecutive heads or tails, so we label them as failures. So hopefully that makes sense what you're looking at here. So essentially, we had 10 partnerships here, and they each did 10 trials. So over on the right-hand side, we have 100 trials. And if you count up the number of successes, there were 78 successes. So there's a 78 out of 100, or a 78% chance of getting at least 3 consecutive heads or tails when you flip a coin 10 times. Now, in my experience, when I've asked my students to make this prediction about this probability, they never make a prediction as high as 78%. It's normally somewhere like 30% or something like that. And that's fine, it doesn't matter. But my point is, a lot of times, you have like a hunch, and then by quickly going out and doing some observations, you can say, wait a minute, if I did 100 trials and 78% of them were successes, probably, if my prediction was 30%, probably I'm probably off, So that's observational probability. Now, observational probability is great. It can give me like a starting point, but this is time consuming. This took my students a long time, and 100 trials is great, but more is always better. So it would take even more time to do more trials. So what are our other options? Well, before we get into simulation, let's talk a little bit more about probability. So a random process generates outcomes that are determined purely by chance. A trial is one repetition of a random process. So for example, we said before that the trial was flipping the coin 10 times and determining whether or not you had 3 consecutive heads or tails. That was one trial. So a trial doesn't necessarily mean flipping a coin 1 time. In that case, it meant flipping the coin 10 times. But sometimes a trial is flipping a coin only 1 time. So for example, if we want to estimate the probability when you just flip a coin 1 time, if we want to estimate the probability of getting heads, for example, this is what we're going to look at here, okay? So in figure 5.1a over on the left-hand side, we have the proportion of heads in the first 10 tosses of a coin. So if you look at this, the number of tosses is along the x-axis. We start at 1, we go up to 10, and the proportion of heads is along the y-axis, right? So if we look at this, the blue line here starts up at that 1. That means my first flip was a heads. So out of one flip, that one flip was a head, right? So 1 out of 1, 100%. And then when I go to my second toss, it kind of shoots down to this green line, or 50%. So that tells me that the second flip was a tails, right? So in other words, I have 2 flips, one of them, 1 out of 2 was a head. So the proportion of heads is a half. And then it shoots back up. So my next flip was a head, it shoots back down, my next flip was a tail. So you can see that this blue line is kind of all over the place. And the other thing you can kind of see is after I have like my 5th flip, it looks like, all the rest of these were tails. It keeps going. I keep, doing tails or flipping tails. And then it looks like I only had 3 out of 10 of my flips were heads. So I only had a 30% chance in my 10 observations, in my 10 trials, of getting a heads. Now, you and I both know that if I flip a coin, the probability of getting heads is 50%, right? We know that theoretical probability. So the issue is that I only flip my coin 10 times. So 10 times isn't a whole lot of flips. Over on the right-hand side, when I jump over here, this is the proportion of heads in the first 500 tosses of a coin, right? So I can see how, like, in the beginning over on the far left-hand side, you can see it's the same. We start off with the same way, and we go way down here. We had all these tails in the beginning. But then it kind of evens off, and it gets closer and closer to that green line as my number of trials, or the number of tosses, goes up towards 500. Okay? So the probability of any outcome of a chance process is a number between 0 and 1. So probabilities are always between 0 and 1. And remember, those are numbers, but we can write these as decimals. We can write them as percentages. So when we talk about percent, you might have it listed between like 0 and 100%, right? That describes the proportion of times the outcome would occur in a very long series of trials. Well, what's very long? I don't really know, right? That's kind of like an arbitrary, we don't know. What does very long mean? But it means a lot, more than 10. So we need a lot of trials, or a lot of repetitions. We need to flip this coin a lot of times. So the law of large numbers says that if we observe more and more trials or repetitions of any chance process, the proportion of times that a specific outcome occurs approaches its probability. So like we said, you and I both know that the probability, when you flip a coin, the probability of getting heads is 50%, because there's one head and there's two options, right? A heads or a tails. So 1 out of 2, 50%. So the law of large numbers says that when I observe more and more flips, as I get closer to 500 tosses of the coin, you can see that this blue line gets closer and closer to the green line. The green line at 50% is my theoretical probability. That blue line that goes up and down, that's my observational probability. That's the proportion of heads when I actually flip. And the more times I flip, so if I took this x-axis out to like 1,000 and kept flipping, that blue line would just get closer and closer to that green line. And that's the law of large numbers. So we can distinguish between estimating the probability of head using observation, and we call that empirical probability when it's not theoretical. We just like found that probability from observation. And we can also use simulation to simulate the random process. And again, it's called empirical probability because it's an approximation, as opposed to a theoretical probability that comes from like a probability model. So the idea of probability is that randomness is predictable in the long run. In the long run. Again, when I flip a coin 500 times, 1,000 times, 1,000,000 times, I know that I'm going to get about, again, if I flip a coin 1,000,000 times, I know that I'm probably going to have close, not exactly, but close to 500,000 heads, you know, in the long run. But unfortunately, our intuition about chance behavior tries to tell us that randomness should also be predictable in the short run. What that means is, like, have you ever played a betting game or something where you're like, oh man, this keeps on coming up like heads, the next one has to be tails, right? That's what we mean by like the short run. So this is actually a really misguided belief. So some people mistakenly use that phrase like law of averages. Oh, it's a law of averages. The last 3 were heads, the next one has to be tails. That's not necessarily true. In the short run, things don't always even out, right? But I know that if I flip over and over and over and over and over, I might have had a string of, 10 heads come out, or 10 tails, or whatever, somewhere in the middle. But if I flip over and over and over 500, 1,000 times, 1,000,000 times, whatever, things are going to even out in the long run, not necessarily in the short run. All right, so let's talk about simulation. Simulation is the imitation of chance behavior based on a model that accurately reflects the situation. So here's a simulation process, and guys, you are going to have to use this process, okay? So step 1, you're going to describe how to use a chance device to imitate one trial or repetition of the simulation. Tell what you will record at the end of each trial. So what do I mean by a chance device? I mean, flip a coin. If it's like a true-false question, you know, there's two options. Flip a coin. Use the heads to represent true, use the tails to represent false. Pulling out random slips of paper, using tables of using digits from the table of random digits, things like that. And then perform many trials of the simulation. And then use your results of your simulation to answer the question of interest. All right. So we're going to go through a couple examples together. In an attempt to increase sales, a breakfast cereal company decides to offer a NASCAR promotion. Each box of cereal will contain a collectible card featuring one of the following NASCAR drivers. I don't even know who these people are. You might. So here's your 5 drivers. The company claims that each of the 5 cards is equally likely to appear in any box of cereal. A NASCAR fan decides to keep buying boxes of the cereal until she has all 5 drivers' cards. Right? It takes her 23 boxes to get the full set of cards, and she's surprised. That seems like a long time. There's only 5 cards that you need. So in other words, she got a bunch of repeats until she got all 5 cards. Does this outcome provide convincing evidence that the 5 cards are not equally likely? In other words, that each of these 5 people don't have the same number of cards, you know, randomly put in these cereal boxes. So to help answer the question, we want to perform a simulation to estimate the probability that it will take 23 or more boxes to get a full set of 5 NASCAR collectible cards. So this should kind of feel familiar, okay? So we looked at very, very similar problems when we were talking about statistical significance, okay? So part A, describe how to use a random number generator to perform one trial of the simulation. So here's what we can do. Assign numbers 1 through 5 is equal to each of these people. And then we're going to use the random number generator. Now you know how to use a calculator. You could use random number generators on the computer. There's all different kinds of things. But you're going to generate, or even slips of paper. You could write down, you know, the numbers 1 through 5 on little pieces of paper, fold them up, mix them up in a hat, and pick them. Something like that. But in this case, generate a random integer from 1 to 5 to simulate buying 1 box of cereal and looking at which card's inside. Keep generating random integers until all 5 labels from 1 to 5 have been appear. Record the number of boxes it takes to get all 5 cards. So that's using a random number generator. I just wanted to throw this in here too. We could also use a table of random digits. We would label the drivers in the same way, and then we would select one digit at a time from the table of random digits, ignoring 0 and then 6, 7, 8, and 9. We continue selecting digits until we've selected all of the digits 1 through 5 at least one time. Count how many total digits we selected until we had each digit at least one time. So imagine going out and doing that process 50 times. So this dot plot shows the number of cereal boxes that it took to get all 5 drivers' cards in 50 trials. So they did that simulation 50 times, right? So the simulated number of boxes required. So a couple times, let's count these, 1, 2, 3, 4, 5. There's 5 dots above the 5. So 5 times, you know, we only had to open up 5 boxes of cereal, or our simulation tells us that we would only have to open up 5 boxes of cereal, right? So explain what the dot at 20 represents. So there was one trial where it took 20 boxes of cereal to get all 5 drivers' cards. So in other words, you had a lot of repeats, right? Okay. Part C. Use the results of the simulation to estimate the probability that it will take 23 or more boxes to get a full set of cards. Does this outcome provide convincing evidence that the 5 cards are not equally likely? Hopefully, again, like I said, this question feels very familiar. So 23 or more boxes. So here's 20, here's 25. So 23 should be like here, okay? So there's no dots at that 23 mark or beyond. So the probability of it taking 23 or more boxes based upon our simulation would be 0. 0 out of 50 of these simulations gave us 23 or more boxes. So there's a 0% chance it would take 23 or more boxes to get a full set. So obviously that's super unlikely. It's impossible according to this simulation. So because it's so unlikely that it would take 23 or more boxes, this result provides convincing evidence that maybe those 5 NASCAR drivers' cards are actually not equally likely to appear in each box of cereal. So now think about it. If going back to my original problem, oops, sorry, I meant to go backwards. If going back to my original problem, it only took her, I'm clicking way back, sorry. If back in my original problem, it only took her maybe like 10 or 15 boxes to get the full set of cards, then let's see how believable we think that is. So going back to my dot plot here, let's say it took her 15 boxes to get all of the cards. Well, 15 boxes, so look, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 out of 50 times in my simulation, 12 out of 50 times, or 24% of the time, it would take someone 15 boxes or more to get all 5 cards. So remember we talked about, like, that's, on the other hand, pretty common if there's a 24% chance of that happening. So that really gives us evidence that probably the 5 cards maybe are, like, equally spread throughout the boxes. Okay? So again, this goes back to that question of, like, statistical significance. All right. Okay, so we are going to go through the first example that we went through. We're going to go back to it. Toss a coin 10 times. What's the likelihood of getting at least 3 consecutive heads or 3 consecutive tails? So we looked at estimating that probability using observation. Now we're going to look at it using simulation. So we're going to use simulation using the table of random digits. So essentially, we know that when we flip a coin, there's a 50% chance of getting a head and a 50% chance of getting a tail. So we have to assign our digits accordingly. So I chose to assign digits 0, 1, 2, 3, 4 as being a head, and then 5, 6, 7, 8, 9 as being a tails, right? You could have done 0, 2, 4, 6, and 8 were heads, and 1, 3, 5, 7, 9 is tails, or whatever, any other combination that gives you 50% of the digits being one and 50% being the other. It doesn't matter. So that's for each individual flip. But remember, a trial is tossing a coin 10 times. So then we're going to go through the table of random digits, picking one digit at a time. So each one digit represents flipping the coin one time until we have 10 one-digit numbers. Those 10 one-digit numbers represent our one trial, right? And then we're going to determine in those 10 one-digit numbers if there are 3 consecutive heads or tails based upon how you assigned your digits. So in other words, 3 consecutive numbers between 0 through 4 or 5 through 9. If there are, we're going to count that as a success. If not, we're going to count that as a failure. So that's one trial. And then from that one trial, we determine success or failure. Well, one trial is great, but really using simulation, we want to simulate lots and lots of trials. So essentially, we're just going to go back and repeat this many, many, many times, 50 times, 100 times, whatever. And then based upon that, we're going to estimate the probability of this happening. So, if I repeat this 100 times and I end up with 70 of those simulations being successes, then the estimate of my probability is 70 over 100 or 70%. Okay? Let's look at another example. So professional tennis players bring multiple rackets to each match. They know that high string tension, the force with which they hit the ball, and occasional racket abuse are all reasons why rackets break during a match. So Brian Lobb's coach tells him that he has a 15% chance of breaking a racket in any given match. How many matches on average can Brian expect to play until he breaks a racket and needs to use a backup? So this one's different. It's not asking me about a probability. It's asking me how many matches can he expect to play until he breaks the racket. But I can still use simulation. So first I have to use the table of random digits and assign digits. So there's a 15% chance of him breaking the racket, right? So I can break up the digits into 2-digit numbers, and I want 15 out of 100 of them. So 0 through 14 would be Brian Lab breaking the racket, and then 15 through 99 would be him not breaking the racket in a match. Okay? So that's within each match, but then I want to know how many matches does he play until the racket breaks. So I go through the table of random digits using 2 digits at a time. Each 2-digit number represents one match. And then I'm going to continue until I've chosen a digit between 0 and 14, and I'm going to stop. So I stop because essentially once I get a number between this range, that represents him breaking the racket. I'm going to count how many 2-digit numbers it took until the racket broke and I had to stop. And that represents one trial. So just kind of keep in mind, like, if the first 2-digit number that I pick was, let's say, a 12, that means that he only played one match and the racket broke on the first match. So the one trial, it would have taken him one match to break the racket. So, and then maybe the next trial, my digits were like 87, 54, and then 02. So that means it would have taken him 3 matches to break the racket. So that's a second trial. So essentially you have a bunch of trials, and in each trial you ultimately have a number of matches that he plays, right? So we're going to, again, repeat this many, many, many times. And then from there, find our estimate of the number of matches he plays until his racket breaks based upon our simulation. So let's say I repeat this 100 times again. So I repeat this process 100 times. Then what I would do is I take, out of those 100 times that I've, gone through this trial, or this simulation, sorry, I would take the number of matches it takes for each one and find the average. So add them all up and then divide by 100, and that's my estimate of the number of matches he plays. So we can use simulation and specifically use the table of random digits in a lot of different ways. So again, we interpreted probability as a long-run relative frequency, and then we use simulation to model chance behavior. So please check out Schoology to find out what you have to do next. Thanks so much for watching. Have a great day.